I'm not going to be able to get to the very end point where I was hoping to get by the end of this workshop. So the scripts that you have there, there's two series. One have to do with an extension of the pop-up grid. Others have to do with the singularities. I'll deal with that later this morning. But before we go there, are there any questions from anybody on any of the issues? I got an email from one of you about the deliverables at the end of the workshop. Still gonna have to see what we want to do. Digital Futures is hoping to have a live exhibition and an online video display of 1 minute of outcome from the workshop. I think we'll discuss on Friday maybe what's possible there from our end. Because what we could maybe do is that people just design very quickly with the tools some of the shell structures, and that we just make like a taxonomy overview. But the main goal of this workshop was to actually do tutorials only rather than do extensive workshop design work. So yeah, let's see how we go about that. Hey, Arihan.
Very good.
Hey, Nighting. Yeah, please leave cameras on. It's always nicer to see people. I know some of you are in the office, but it's easier to talk to faces rather than to blank names in Zoom. Any questions?
Hello.
Anything that was covered on what we said? Any questions on what was covered yesterday? Hey, shall I just get going? Okay, I'm going to share the two files once more for the people that just joined. And then if people join in later, yeah, just let me know and I can add the files again. So we're going to start with the pop-up grid continuation. And then after that, we're going to go into the singularities. Okay, let me share my screen first. So we can build up from the script that we had made yesterday with the pop-up grid. So that one, as you remember, we started off, I'm just going to reactivate it because I didn't embed the curves. We started off from a basic grid. Let me just make that one 15 by 15, say, or 100 by 100 then. And that's going to be our, hold on, let me lock this for a quick second. That will be our square to subdivide. And then we're going to put a boundary in there. That will be the pulling curve that we're going to bring in. Too many points there. I'll make that one my curve. Set one pulling curve. Oh, my boundary is not yet set. Okay, so this is what we had yesterday, and if everything goes well, why is everything not going well now? Oh, this one is not yet set. Boundary. Oh, this one is exploded. Oh, this is the surface. Okay, hold on. Duplicate border. Yeah, my bad. Set one boundary curve. There we go. All right, and let's see if I switch this one on. This one should, if everything goes well, create my pop-up grid with surface. Let's see how it's going. So the first script that I gave as part of the zip, and again, let me know if people have joined and that don't yet have in the chat the zip files. Please just let me know and I'll re-share them. Let me open my chat here as well so I can see it. Yeah. So the first script, oh, this one is jamming in a weird location. That's funny. Hold on, let me, this should normally work. I don't know what's happening. Let me use the zombie solver instead, just so that we can jump to a conclusion. Okay, it's calculating. The first script that I gave you, which is 7A prefab, in one go gives you, okay, so here we have a nice clean shell that's coming from it. The first script that I gave you, 7a, actually, let me open this up here right now, and it will now again, this one will automatically in one go also give you the prefab flat grid that you need. Let me just show you how that one is done. I'll switch it on to the zombie filter so that we have a result faster. Yeah, that's all good. There we go.
Here. This will be better.
Hold on, why is it still calculating? Here we go. So what I have here now is in one go, I have the popped up grid, and then in one go also the flat grid on the ground that needs to be fabricated as part of it. So there's a tiny little part here that's been added to the setup. So let me just explain what I have changed in this script. Not too much, so we still have just our surface coming out as a whole. I unflattened that one over here so that we basically can work separately with the curves that I have here and then the mesh over here. And this is the lofted surface that we made yesterday that was going through. So the upper part is totally identical of what we had before. But what I did is I started working with these curves here at the bottom. And so here I have my deformed network. Here I have my flat network that we started from in the very beginning. So that's what I've been dragging in here for my distance comparison as well. So I have both of these in place. The first thing I did is I just identified the intersection between this network and a plane, for example, a ground plane on location 0, which is what this one would be. And then what I get is the parameters t of all of these curves where they intersect with the ground plane. And then, so for all of these curves, I actually have 2 intersection points. Let me just highlight that. I have 2 intersection points for this specific cell. Like, for example, curve 0, which is entirely underground here on the right, that one does not have any intersection point. But as soon as we're in this curve number 1 here, there's 2 points where curve number 1 intersects with the ground. So that specifies a domain that I can use to then basically derive a subcurve from my original curve set. So that's my subcurve that I've taken just by intersecting each of my input curves with a cutting plane that's on the ground here. This is a very quick calculation because curve plane intersection is a mathematical formula. It's not a physical analysis that you really need to do, so it calculates quite quickly. But then the funny thing is, or the fun thing is, because our curves, yes, I'll share the file again. The PDF from yesterday, John, is incredibly messy. So if okay, I'll just give you the files. Because in the PDF, it's based on old scripts that I'm actually correcting as I'm teaching this course here. So if that's okay, I will, I can send it to you later once we have everything corrected and optimized. Okay, here are the 2 files again. So I'll rework this PDF. It's really, really a dirty draft to become a final booklet in due course. It's going to take me a little while to get there, and then I can share it back to everybody here. But that might take a few months actually. But you'll have the scripts. So, sorry, back to where we are here. So, hold on, I'm going to mute somebody. Yeah. So, because we have this domain for our bent curves in place, but the curves have exactly the same topology as the original flat grid that we have, we can actually identify here what the flat grid would be that we need to produce. And that's quite interesting because you see that there's actually not that much length difference between our bounding curve and the grid, but it's not identical. And then another thing that helps in identifying exactly where our surface hits the ground is just to intersect the mesh with the same plane. So right now you see that's actually where our foundation line is going to be. So this flat grid that we have produced here will eventually be pulled to that brown line that you see here, or that orange line, to produce this grid that we have. Yeah. So super fast. Like to produce a grid like this, all you really need is these type of end distances. Like you make a regular grid and then you just saw it off based on the distances that you need. And that's it. You're basically done. And with HoloLenses, that would be super easy. So that's the first one. A very, very quick fabrication tool that's been added. Any questions? No?
No, good so far.
Yeah, all good. Quick thing to point out, my scaled down curve to which I am pulling with all my anchors. So remember how we're making, we're pulling all the points from our mesh that is over here. Oh, all the points from our mesh that are over here. We're pulling those points to these points on the curve with a very weak spring force. So it's not a hard connection that we get. And because of that, we still have kind of a relaxed edge. Like if you would make these points super tight and super hard, then your grid will distort quite a bit around the perimeter. So I'm just bringing this up again to highlight that the tools that we're working with here are operating with a level of flexibility that you would have if you would make this with a physical model. You won't be able to very, very rigidly put everything into the exact control point that you specified as part of your anchors, because your anchor line actually sits over here. You see that the balance, the equilibrium that we find sits a little bit off of that. And that's how we can design and produce it. Now that becomes a challenge when you're working for a very precise and specific site. Like if you want your edge to be exactly on a certain curve that you have, then you need to tighten the strength of these pull forces, and then it might give you a little bit of difficulty because the grid might start to glitch a little bit. That's one of the reasons I believe why Friotto's structure also works very well. It's in a totally open field, and it doesn't really matter if your boundary is half a meter left or right or 20 centimeters left or right. But here in the design tools already, you see that it's quite essential that you have that flexibility for the grid to eventually work. Okay.
So one question.
Yeah.
If you're trying to use these anchors as a hard goal, that means you're trying to force it to behave or conform to a shape, a predefined shape.
Yeah.
And is that something wrong in terms of designing method?
I've been thinking about that last night, but I haven't been able to implement it here. There is a goal that you can have here to pull to curve, I believe. And I forgot where that one is. But there
is points on curves. I think it's goals over here.
This one here. Keep a point on a given curve. So what you can do, so that's basically like a sliding anchor. It's like you have a rail and all your points can slide along that one. That would probably be a better way to do that. And then you make it super tight, because then at least along the tangent vector of the curve itself, there's a degree of freedom. So at least there your points can be shuffled a little bit. But you'll need to be careful, because the original, like we're basically pulling all of these points and they're not on a line either. So if you would make that one too tight, you're basically going to crush your grid in that area onto a curve, and that doesn't work. So you need to be careful with that. What I've done in the past is do a few iterations. Like first you do the one that I have here, which is approximate. Then you bake that one, or you internalize the data with the structure, and then you run it again through a Kangaroo. And then that time you do it with very hard anchors. That's also possible. So that you run it a few times and use the first time to get your approximation of where you need to trim your grid, and then your second time to tighten it up. That's also possible as a strategy.
Yeah, but coming back to this point I was making, because this is not really showing what Bamboo is, how it is going to behave. This is just a simulation to achieve a form, correct? Yeah. This is not really simulating Bamboo's behavior. So
this is like, we've used this to make the bubble shape with Bamboo that I mentioned before. So all the curves have a similar spring force, like an angle strength straightening force.
Yeah, agreed. I mean, you can I mean, we can still keep these forces constant,
Yeah.
and I can still have additional constraints which can guide the way these curves will behave. For example,
Yes.
all the grid points, if I see it in plan, they can remain in the same line as they are in the initial grid. It just moves in z. So each point I can give a goal where each point will just move in the z axis and not in the x and y axis. And it can still maintain the lengths. It can also still maintain the spring and every other thing. So what I'm trying to come at is if you have a shape which is slightly deviated from this one,
Yeah.
derived from kangaroo, and because we are going to be flattening it out into a grid, that means technically we can make any shape. Because ultimately we are going to flatten it out and make it out of bamboo, right? Because kangaroo tries to reach an equilibrium, we believe that the equilibrium is trying to get us a shape where all the forces will be flowing perfectly. But if kangaroo gives you something which is also forced in a way in terms of constraint and it reaches an equilibrium, that should also kind of stay. Am I being clear in my question?
Not 100%. Say it again. I'm not fully following.
Or maybe we can take it up later. I don't want to break the flow.
No, it's fine. It's fine. I mean, so
probably what I can do is I have some scripts which I can show you where it will be apparent what I'm trying to mean when I say creating deliberate shapes out of kangaroo.
So I've been working. I don't have that prepared for today, but I've been working on tools where you model any surface and then you populate that with an equidistant grid by having a running algorithm that just subdivides a mesh iteratively. And that works. You can basically project an equidistant grid on any shape, but that doesn't, and then if you then put it into kangaroo, then you'll still see that it will deform a little bit, and it will deform entirely based on two things: the topology that you have and the boundary conditions that are anchored in place. So if you change your topology by lengthening parts or by having a denser grid, or by then the bubble shape in the middle will change. And if you change your boundary, then the whole setup will change. But in principle, the only thing that defines the geometry that we have arrived at over here is the topology of the grid, which means its number of cells and the distance in between them, and then the end parts, how long they are, and then the exact location of the anchors, which here are presumed to be hard, fixed on the ground. And there, the forces are not even as well. Like if you would build this one from bamboo, it's possible that it kind of will have its edges popping up, because maybe it's pushing harder in the middle than it's pushing at the sides. So the anchors are quite essential. But so you can approximate many geometries, but you cannot make any geometry from bamboo. It's almost like or from a bending active shell. It's almost like a balloon. If you'd stick a balloon through a ring, it will take its balanced shape, but you can push it in one point, it will just deform in another part. Or you can put a tape over it, and then you'll get like two bubbles. And similarly with these types of structures, you can put a metal cable over it and tension that cable to create a deformation. That's all possible. So you still have quite a bit of flexibility to play with.
Okay.
With the Z coordinate fixation, there you need to be very careful, because if you lock something in the XY direction, then automatically the minute something moves up or down, your lengths will change. So you will create a setup where the balanced equilibrium will incline towards a change of length. And it's a change of length that with a rigid equidistant grid becomes quite difficult. That's when you have tension concentration that will break the grid. Does that answer?
Yes. So none of the structures that you have already shown us in the presentation that has already been constructed, none of them had unequal distant grids towards the end of the structure? Like when it was deformed?
Yes, exactly. Well, no, I showed two types. So the ZB bamboo pavilion, like this one here, that was entirely non-equidistant, because that was done one stick at a time. That's a layer method. That's different. The Fraiotto pavilion and the smaller bamboo bubble that we made with that, that was fully equidistant. So there's no sliding there during the construction.
All right.
And theoretically, in reality, the two poles can still roll a little bit over each other. So there's always a little bit of flex that you need.
I think there's a question on chat.
Yes. Hello, teacher. I have a doubt. the best type of structural analysis for system is the nonlinear one. I understand there are several second-order parsing algorithms in grid shell systems. How does a grid shell behave under seismic forces? I'm not a structural engineer. I cannot answer that one. I know I don't have the knowledge to answer that one. We can talk later in Karamba, hopefully on Friday, what we've done. And I know that it's an abstraction. Like we need to have some structural engineering still at the end of this. But it's all of the tools that we have here right now are just an indication. So yeah, Enrique, I don't know if I'm answering this one correctly. We do have, yeah, we've collaborated at one point with some structural engineers to advise on some of these things, but this is more of an architect's pseudo structural engineering science to get the designs to work. And then so far it looks like the built outcome response to what we've been sketching out here. So yeah, cannot answer that one. But good questions. That's what we need to look at in the future. I mean, the seismic forces, in principle, they behave quite well through it because the system remains in an equilibrium, right? And it has it has a setup through the hinges that allow it to move and wiggle around a little bit. So that elasticity of the shell allow it to very flexibly, elastically adapt to whatever load conditions that you have. It changes the minute you put a high tension fabric on it that is tailor made, because then that basically locks the mesh and all the diagonals into place as well. So that's incredibly stiffens the structure. And also the diagonals that you would add to it, that also stiffens the structure. Which actually brings me to the next exercise, how to put the diagonals in it. So let me open part exercise B here. I'm going to have to reconnect that again to my input, which I should have added from the very beginning. And this one. Oh, what's happening? Oh, yes. All right. Yeah, oh, this is with the live one. Actually, I should do it with the. No, hold on. Let me do it with this one. It's gonna be easier. Yeah, it's calculating right now. So now what I'm doing here, we add a little trick on how to get the diagonals added to it. It's quite straightforward to get there. Hold on, let's see what's coming out here. Okay, so what you see here now on top is the same bubble that we just had, that I showed earlier with the top grid and then diagonals added to it. And I added a simple toggle that allows you to flip the diagonals from one direction to the other one. So how did we get there? Let me open that up first. Hold on. So here on top, there's a new part that I added. So if we have our mesh here, this is a surface mesh that we had created that was the skin of our project. If I add the edges of it, that's the mesh that we had. And I made a very simple script that basically explodes every mesh face into unique faces. So the whole mesh into unique mesh faces. Then I extract the vertices from all of them. And then I'm just drawing a line. It's all quads between either the first and the second, the 0 and the second vertex, or the first and the third vertex. So I'm either drawing all of these lines or all of these lines. And then because these are planar and interconnected, I can just join them to be my curves in the one direction or in the other direction. So that's very straightforward. Those are polylines that use the same vertices as Kangaroo is already using in its calculation. So it doesn't add any calculation time to the Kangaroo algorithm to find a solution. So all you need to do is actually add that, merge that into your show button that I have added here in our goal objects for Zombie Solver. So you can add whatever you want here. So this whole show button, what it basically does is it redraws geometry that you put in there through the control points that you have running through your algorithm. So it just keeps track of the order of control points that Kangaroo is calculating, and it's reusing those to draw the geometry that you put in there. So that's how we've been doing the members, how you've been doing the mesh, and now how I'll be doing the diagonals. Then at the other end of the calculation, after you unflatten it, it basically keeps the data structure intact that you have put in here on the beginning. So first and second branch, or well, branch 0 and branch 1 will be my diagonals, branch 2 will be my mesh, branch 3 and 4 will be my diagonals that I have. So branch 1 and 2 will be the main members, UV, and then 2 is the mesh, 3 and 4 are the diagonals that I'm working with. So after my calculation, here, let me just show this. So after the calculation, I basically get my curves in the U direction. Let me switch that all off there. Nicely deformed, or my curves in the, well, the W1 or W2 direction, nicely nested inside the grid that I have here. And then I just added a little toggle here at the bottom to basically navigate between the ones that you want to have. It doesn't really matter too much as far as I can tell. And then similar to how I was cutting my base curve grid, I'm using the same plane, same XY plane that I have here to cut my subcurves here. I'm using the very same plane to cut my diagonals here. And then, yeah, here after cleaning it up, I have my curved three-dimensional grid. And then the only thing I'm doing after that is, let me quickly see. Yeah, measuring the lengths and producing polylines on the ground here according to the lengths of the diagonals that I have produced over there. Similar to what we did yesterday when I was doing the unrolling. So nothing too complex there. And then I just added 3D tags to the three-dimensional diagonals here. So here you see the order and the ones that we have at the bottom. So it's a very quick system because we're just relying on the control points that we have drawn up already. So it's quite straightforward to do. So for the very thin bubble that we did in the rooftop garden of our school, this is a technique that we used. We also later on offsetted all the layers, and I'll tell you a little bit more about that towards the end of the day. I haven't fully completed my preparation for that one, but we'll get there towards the end of the day. Any questions? Pretty straightforward, right?
Yeah, I have like technical question. When you add the diagonal members,
yeah,
do you like create two nodes? Like one, you have the original node in one direction, and we add the other one in the other direction. I don't know how it works.
Yeah. So normally, if you have one pole and then another one coming underneath it,
yeah,
oh, I'm drawing it very badly. You would kind of make your tie around it like that.
Yeah,
it's very coarse. And then indeed, if you then bring in your diagonal and you add another member running through it, say, yeah, then that one needs to be tied over the whole thing as well. But so in elevation, you would have yeah, something quite thick like that. You'd have your first knot and then your second knot over it. So that means you're starting to get quite a bit of movement potentially there. It becomes quite loose. And that's why, yeah, but that's fine. That works. If you have the knots that they're making here, basically tighten themselves up. So what they do is they have this technique where you put your wire around it, and then you start to wind it. And as you're winding it by hand, the knot tightens itself up. And at the very end, you take the end parts of your rope or of your wire, you put it underneath and you slide it underneath the bamboo and the wires again to tighten it up even more. So there's it's a very interesting, it's like a Boy Scout knot that you would use if you would make your tents or whatever. So it's quite a standard knot that tightens itself up a little bit. If bamboo shrinks because of humidity dissipation, then you might need to go around and retighten a few of those knots. But yes. But so what this also shows is that eventually you're going to have three layers: your base layer, your top layer, and then your upper layer, all spaced with the diameter of the bamboo columns that you have on average, right? So eventually, and we'll end there today. The trick is how to offset all of these layers. I mean, for a simple bubble like this, that's not too difficult. Actually, I didn't prepare that file. Let's see, maybe we can do it later. It's pretty straightforward because we have the mesh over here. We have the mesh over here, which means that we have the mesh normals, which means that we know exactly how to move things up and down in which direction. So we can just take our original curves and move the points according to the normal direction with first one column diameter and then another column diameter, and then we'd be good. Actually, let me see. Let's see maybe how fast we go today towards the end of the morning. Maybe we can add that offset thing. I have it done for the singularities because that's a bit more tricky and complex, but for this one, it's actually very straightforward. Yeah, well, we can do that maybe by hand at the end. Yeah, other questions?
No.
Yeah, somebody mentioned want to see a video of how we do ties in Hong Kong. I have a draft somewhere. Let me see if I can find it. We have started making a video because there's 3 types of knots that they're using, and I've gone with the team to the scaffolding school where we've been filming it from different angles. Let me see in the break if I can pull up the video. If I can find the knot video, I'll show you right away. We haven't released it to the public yet because we haven't finished the editing. But I'll see if I can find a draft of it. I can show you maybe over after the break. Okay, then tie direction. That's the last one that I wanted to add. So let me close this one. No, close this one. No, close this one. No, and I'll bring in the C file, which has to do with the tie direction. So I need to reset this again. Oh. And let me again do that with the zombie solver. It's faster. So what I was mentioning yesterday is that you have to be wary of how your structure will deform because you will either tighten up your knot or you will loosen it. And if you tighten it up too much, you risk that the structure actually would break the wires. So there's a delicate balancing act there. You kind of want things to be tight, but you cannot have them too tight. So we haven't done the practical calibration of when you really need to shift. So what I've done here is I've written the script on what to do to prevent the knots from becoming even tighter. So all the knots are actually becoming a little bit looser in this setup. So what has changed from the previous script? Nothing here, nothing here, nothing here, nothing here. It's entirely afterwards. So actually we don't need the diagonals even. Yeah, this is actually something that would be done without the diagonals. So forget about that part. So let me switch this off. Let's first do it in 3D. So here we have our original grid, and it's actually quite straightforward. First thing I did is identified all the intersection points, which we already had, but I just re-identified them because what I'm doing here is I'm finding for each, so with this MCX button, the multiple curve intersection button, it shows me the first curve it intersects and then the value t on the first curve, and then the second curve it intersects and the value t on the first curve. And this is interesting because then you can evaluate your point on those curves and get the tangential vector for it in both directions. And then with those, you can basically draw your planes. Hold on, let me display plane size. I'll drop that a bit. Okay. So now you see that I've drawn all my planes on all of my curves using the red line, the x direction, to follow the primary curve that we're looking at. And here you can start to see with the green line there, the y direction, where the angles are more or less. So this is my plane here. So then what we then can do is in this plane, we can measure the angle between, and let me display the vectors for a second, between my first vector, which is this one, and my second vector. Oh, come on, why is that not working? I'll just do it like this then. And my second vector. Okay, so that's the red one and the green one now. So we're basically calculating the angle between these two. And then we can decide whether or not that's more or less than 90 degrees, pi over 2. So what I'll be doing is I'll be creating two types of grids in which we can put a knot, either this one or this one. So for each point, I'll first identify these two perpendicular grids, and then we'll select which one to work with based on whether or not my angle is smaller than pi or 2 over 2. So the plane that I have here, I'll start by rotating that one according to the angle that I have, according to half of the angle that I have here. So we arrive at these types of planes, which you see that now they're oriented towards the bisector of our plane here. And then I'm just going to deconstruct this plane. Hold on, I'll put in perspective so you see it a little bit better. I'm going to deconstruct it in X, Y, Z directions, and I'm going to recreate these planes on top of it, just using my X, Y, Z values. So what I have now is a perpendicular plane based on my bisector. And then I can just, depending on whether or not I'm smaller or larger than this one, I can select my 0 item or my first item very straightforwardly, and I basically arrive at my final plane here. And then I can put a circle on it. So that's that, very straightforward actually. So if I look at that, let me switch off a few things here so we can see it better. What this does, let me delete these. Yeah, like here you can see the transition quite well from one direction where it's very clear which one is the wider angle to the other direction where it's maybe less clear. So you see the transition spaces and the orientations that we have. Yeah, that's a very, very simple trick just by looking at the tangencies inside each point. It took some time to figure out the most elegant way to script this, but yeah, this is
I think there are some opposing directions. Can you just zoom in? Or on the left, yeah, just over here, yeah, zoom in. So there are diagonals are in opposing direction over here.
Yes, like here, for example.
Yeah.
But that's because the grid is slowly deforming from square to diamond shape. So at some points, things will start to, change.
But okay, I was of the opinion, like in the way I understood, and may I just annotate on it?
Yeah, go ahead.
So the grids that we're following, the diagonals are like this, right?
Sorry, this is for the tie connections, right? Here we can choose in which direction we put the diagonals. This is just on how to tie our original 2D grid.
Okay, so so we have one kind of tie for the original grid, and then for the okay, this is just for the original grid, not for the diagonal.
Yes, it's just for the original grid, because those are the ties that deform with the whole structure as we keep on going up, and it's to prevent those from snapping. If a 90-degree angle becomes very tight, it can either break the bamboo if it's metal wire, or it can snap the tie if it's like plastic.
Okay, so it has nothing to do with the diagonal direction.
No, this is the first knot that we have. And then on top of that, indeed, we can then add whichever diagonal we want to have. But that's totally separate from it.
Okay. Usually all three directions, I'm sorry. Usually all three directions are tied together using a single knot, or
no.
When I say three, okay, no.
So the way you would build this one, hold on, let me wrap up the exercise first, and then I'll explain more. It'll become maybe a bit more clear. So just like how we did that in our deformed grid, on our original flat grid, we can also make all of these rotation planes. We can also create the two angles, but here they're all exactly the same. And then what we can then use is the same angle measurement, the measurement that we did in 3D. We use that measurement to again filter through our flattened setup. And then we get something like that. So now you see what you would do is you would first build this grid with your ties in this direction. And then this grid, once it's deformed, it will pop up into a bubble shape. None of the ties will snap because all the ties will become a little bit looser as they go up. If I were to choose that as a strategy. So now everything will move quite loosely. And then once it's popped up, then it will be like this. It will be like this. And then once we have that built and that works, then we'll just add diagonals, and it can just to stiffen the whole thing. This one or this direction. You can kind of choose what it is that you want to have. So that's the second knot. So you don't add the diagonals until your whole system is deformed, because diagonals lock everything in place. And actually, to add the diagonals, I don't even know if you really need to simulate it, because theoretically, without them, your shape is a bit loose and bubbly, kind of, let's say. You can just put a stick over it and trim it at the end wherever you want to have it, and then you cut it, and that's it. But the prefabrication lengths that I showed you here earlier, this kind of helps in identifying ahead of time exactly what you need. But it has to be done with a little bit of tolerance. So that's what's being added afterwards. But we ran into a problem actually when making study models. Hold on, got one here. So let me switch off my fancy Bamboo background, which is not needed. Oh. Hold on. So in this is a model, an early test that we did that was made with zip ties. Very simple, small zip ties. And we started to realize that as we deformed them, as we deformed the grids, they will all start to snap. Only in certain areas. And that's when we started to realize that actually it's the connection that we have. That's a problem that needs to be resolved. So yeah, so this informs, so basically what you need to know on site is this. Hold on. This is all you need. Basically, drawing that says where you need to tie things, and you can imagine with a HoloLens that's very easily projected. And then these drawings for your diagonals, and then that's it. You can build up the whole thing. So those are your construction drawings to make this bubble, and then also this line for your foundation. That's what you need, and then your bubble will fit. So the way we did that. Let me see if I can find a fun video of that. Yeah, I haven't shown that yet. Give me 1 second. I've got a very nice video of the mock-up. No, I don't. Sorry, it's a different project. The way we did that is we built a grid. Then we lifted it up on some tables, and then we just hung on the sides of it and slowly pulled it down all together. We added a rope around the perimeter, slowly tightened the rope to basically tie the whole structure down until it would hit the ground. And then we fixed it to a base ring that we had made. Okay, any other questions here? No, all good. Okay, cool. That's it for the pop-up grid. So this is a hybrid system in a way that you start from a flatbed grid that gets popped into shape, and then the diagonals kind of strengthen the whole thing. But as I mentioned yesterday, this is quite restrictive in terms of the types of geometries that you can make. You can make all kinds of bubble shapes, but that's about it. Like let me just quickly, while I'm talking, just to show the extent. If we take this curve, say here, and I'll start to deform it a little bit into something more extreme. Like this is probably as far as you'll be able to kind of change your setup. So let me see what happens if I try to create this one as a bubble. It's really like a soap bubble setup. It doesn't give you too much flexibility. Let's see where we end up after the calculation is done. So that's why we developed the singularity idea. I'll start to shift in that direction now. I've worked my way through quite a bit of the tools, but I'm not yet at the very, very end. So we'll leave some for Friday, but quite a bit of the tools are already there. So what I'm going to show you today is how to work with the setup, then how we can use Anemone to join all the curves. Let me see what this one looks like in 3D. Yeah, so it kind of looks like this one, and you see that automatically it will kind of flatten in one area there. But yeah, that's still a pretty nice bubble shape, actually. Still work quite well if you would want that. So for this next thing, you need to install Lunchbox. I forgot to mention that earlier. I mean, it's a very common plugin, maybe you haven't installed, but Lunchbox has one diagonal diagrid button that we're going to use. It's just a little bit easier to use that one than to write it entirely ourselves. So I've just rehashed that one. So no need to save this one. So I'm going to shift to script 8A that we had, and I'll start with, I opened the Rhino file, single column, which is this one here, save changes, no. Okay, so to start, I'll first explain the concept. So what we're gonna do is, this is a topology definer, say, and again, it's not rocket science. It doesn't do anything that it wants to, that it potentially can do. But what we've created is a system where you work with three main orientation planes, A, B, C, or X, Y, Z if you want to. And these planes, importantly, all have exactly the same orientation. It's basically the same plane that you copy around. And then the idea is that we use these planes to generate diagrids on it. Then we'll use Anemone to connect all the curves together. And then we'll bring that into Kangaroo, and then we'll pop into Shape. And then we'll go through all of the challenges of offsetting, putting your mesh through it, creating diagonals, etc. So we'll see how we go. But so the idea is that with this setup, that's basically your starting point. And then if you want to, you can continue and expand it very easily just by copying exactly these planes. And then like this one, you'd have a double column setup if you'd want to. And then, of course, you can also later on always add lines to deform this or to pull things to the foundation or add anchors. Like this is the equivalent of a neutral shape that can then be deformed. So this becomes really a design tool now, but the design actions that you need to take are actually quite restricted. You only work with the topology that you have here in the beginning, and then you add constraints further down the line. So I'll just start with this very, very simple column, and I'll open the first script, which is 8A singularities. So what I've done here, very straightforwardly, I have a pipeline in place that reads all the surfaces that I have produced on the right here. This means that I can always very easily just add another one to it, and automatically the script will recognize it. And I'm starting by parsing out the three sets of surfaces that I have into three data branches. And then I'm turning those, let me hide them here now. Then I'm turning those into surfaces. Well, I'm just making sure these are reparameterized surfaces. And then I'm using the diagrid button from Lunchbox to basically turn this into a diagrid. And that's what you see here. It's an equidistant diagrid. Now, the reason why we're using this one is there's different ways of doing diagrids. The nice thing about this button is that it immediately produces one that's not touching the corners. It's kind of away from the corners. And that allows us to basically generate these singularities, these equidistant singularities at the corners that I have here. So right now you can already see this one produces a pentagon over here. Sorry, that we can then later on work with. You can change your density of your grid very easily over here to very coarse or very fine. So this again gives us some level of design flexibility. Now I know that this is a little bit restrictive. Like currently all my surfaces have the same subdivisions. You can also work with rectangles or split it in half. Like there's a lot of things that you can add to this to make it more flexible as a design tool. But this is already quite something, I believe. So let's just start with the basics. So then the first thing that we do is, let me just show you the data structure that we're getting out of this. So I have my surfaces, I'm grafting them all here. And then as an outcome, I basically get for each surface, my 16 lines. And we found that the data structure is such that if we just bring it back, is such that you can easily partition it with the number that we have here. So let me show you the partitions that we're getting. So branch, 3 branch, item, list item. Let me just show you what we're getting here. Oh, sorry, this one, this one. Where are my curves? Why are they on here? So this kind of sorts the data like this in little zigzaggy lines, which is just the way that data is set up. So what we can do is basically dispatch this in two directions. Branch A, which is all of these, and then branch B, which is all of these, is just the reality of how the data is structured in the lunchbox button. And then you can see that we always have one line in one direction, then in the other one. So we can easily dispatch this into all the lines in one direction and then all the lines in the other direction. And then all we need to do is basically join them. We just need to be very careful that we don't yet join them across the surfaces. So right now my data structure is still keeping my X, my Y, and my Z direction in place. So let me show the data structure here. Path, hold on. Let me make a quick visualization button that will help. Data, path, data. Okay. So this basically keeps my data still all the X directions, all the Y directions, and all the Z directions. And these I can join because I'm sure that I'm not going to make any mistakes across the edges here, because the difficulty is what happens, how do you connect this line? Do you connect this one with the one that goes back here, or the one that goes down, or the one that goes in that direction? So in each of these points, there's actually 3 ways that we can connect everything, and that will become the challenge in Anemone further down the line. But what we do know is that within each of these X, Y, Z directions, we can definitely join all of them and we won't have any problems. So that's kind of what's happening here in the one direction, and then here in the other direction. So what we have as an outcome at the very end here is basically for each orientation, so topology A, topology B, and topology C, we have the diagonals joined in the U direction and in the V direction. Yeah, so that's the outcome that I have over here. So let me just bring that in. So just to show, so the first branch is this U direction in, U direction in X, U direction in V, topology A, one direction, topology A, other direction, topology B, one direction, topology B, the other direction, topology C, one direction, topology C, the other direction. Yeah, so it's all very nicely structured. Hold on one quick second. Yeah, so that's the starting point of the whole setup. And then the challenge becomes, as I mentioned, how do you join these? And there, I have to say, for a long time, we would just do it manually. We would just manually select the lines and join them according to the direction that we wanted to have, because there's so many different conditions. But then after a while, we managed to write the second script with Anemone. So let me open that one up. Any questions on this? No, right? Pretty straightforward. So the nice thing about this is whichever topology that you'd be working with, and let me just open up a different Rhino file here. So I'm opening the W shape here. Nope. Yeah, so for this one, this kind of works as well. So it's a different input setup, and you see now it's creating a hexagon in the middle, and you can increase the resolution to as high as you want to have. So it's kind of a flexible script that we have, but we need to always work with these types of topologies. Okay, let me go back to my column and let's go to the second script. No, okay. Okay, so the second script, B, is where we join things with Anemone. And this is it's a fun one. It's a challenging one. So let me just show you what happens. So I'm drawing here NURBS curves through my points because that kind of shows the wobbliness already. And I've color coded them based on their length because that helps in kind of identifying if we would have made so many mistakes in our joining. So here you see that my lines have been connected correctly. It just hasn't been deformed through Kangaroo yet. So these are just NURBS curves going through the points to kind of show through the wobbliness what's happening. And then later on, we can bring those into Kangaroo. So what I've done for that is a very interesting strategy, actually. So let me go back here. So here at the bottom part, we have our curves that I just mentioned. What we did is we kind of found in our surfaces, let me highlight those as well. So those are the surfaces that we have. We have joining issues only around the inner edges between two types of surfaces that are not of the same setup. So it's only around the points here that I need to join, here that I need to join. So what we did is first identify the points where we actually need to make a joining challenge. And then we have our list of all the curves that we have to look at. And then what Anemone does, it basically creates a loop. And what it does, it goes through all of these points, each point that I have. And then for each point, it will evaluate which solution is the best. And typically, the solution that is the best is the one where the curve continuity is the straightest. So what do I mean with that? Like if I look at this point over here, for example, logically, we want to have this one connect and that one connect. Because if I were to connect this one here, I would have a sharper angle in my curves than I would have otherwise. Now, there's three ways to connect. I could also connect these curves like this. But again, the orange and the green would result with sharper corners than if I would go for the red solution. So the way I wrote this script is it will circulate through each of my live points. So all the points where I need to make a joinery. It will look at my bag of curves that I have, which is continuously improving because I'm continuously joining. So it's step by step, I evaluate one point and I join the curves there. So the curves that I'm working with, they change over time. In the beginning, they're all loose, and then gradually they'll be connected. So my curve list gradually changes over time until everything is connected. And what I do is, step by step, I evaluate each point. I look at the angles of the vectors around that, the angles between the vectors of the line segments that arrive at that point. And then I join the ones that have the biggest connection between them. And then I update my point list. I say, okay, this point, once I'm done, I'm basically saying this point no longer exists. The curves that I originally had, which all stopped here, are removed from my curve list and are replaced with the continuity curves that go all the way around it. And then I repeat it, I go again to the next one. Is the concept kind of clear? So there's basically two things that I start with. A bag of points, which are my live points, and then a bag of curves, which are all the curves that I have. And the first thing I do is I take my first point, which is, say, this one. I identify from this list that I have here, which curves end up in it. Then I join them based on the way that I want to have them joined. And then the four curves that I had originally in the list are being replaced. So these four curves that I have are being removed and replaced by the newly joined curves that I have. So my curve list is gradually shrinking in size because curves are being joined one point at a time. So once I've done this for my first point, then I jump to the second point, to the third point, and to the fourth point. I'm actually not jumping to the second point. I'm actually deleting the first point from the list. And I'm going to my new first point, which is the second point. Now, once that's done, I'm deleting it and I'm going to my second one. Is the concept clear? Kind of?
Yes.
Okay. I know not many people that are scripting in Grasshopper only have experience with loops. So Anemone here has a few ways to loop. An easy way is to just have your loop start and your loop end. So what you do is here in the beginning, you put in your number of iterations that you want to have. You can make as many as you want. And then here you have your data that you want to use, and you can expand that as many times as you want. And then basically what you do is you connect data to data to data. And in between here, you can put all kinds of operations, whatever you want. So now what's going to happen, it's going to loop through this. It's going to use all its data. It's going to perform these operations. And then the outcome is going to go back into the beginning. And it's going to go back into the beginning. So it's going to keep on doing these operations here. And this is where I'm going to delete points from my list, replace curves with interconnected curves. And then at the very end, you're going to have your final outcome once your loop is done. Here, you can choose to end your loop at a certain amount of iteration. I mean, there's different ways of that's the basic concept. Whether you use the classical one or the fast one, they're both similar. Yeah, they're both similar in the amount of iterations that you're working with. There's other plugins that do this, like Hoopsnake, but Anemone is really nice because it updates automatically. You don't need to have any buttons in there. If you change your input geometry, it will automatically run through the whole script. So it remains a live button in your Grasshopper environment, which you need to be careful of because it takes quite a bit of calculation time potentially. Like you can let these loops run for quite a while. So let's go here in the very beginning. So I have all my points. Oh yeah, so first I need to identify my points on the edge. So let's see how I did that. So hold on, let me switch this off. Switch this off. So I have my surfaces here. First I'm doing is I'm joining all of them and I'm finding the naked edge curves, which are all of these. So by joining the planes without flattening it, I'm joining all the let me switch this off. I'm joining all the topology A planes, topology B planes, and topology C planes, and I'm automatically getting all the edge curves that are relevant. Now I need to make sure that I get points that are inside. Let me see how I did that. I'm dividing them at the kinks, right. And then I'm exploding them. Let me see what I've done here. Right, so currently, if I look at these curves, this is actually the one on the top here actually consists of 3 line segments. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And I want to change that to become 1 segment, 1 segment, 1 segment, 1 segment. So the way to do that is I'll take my continuous polyline and I'll only divide it at the kinks. So if you switch on your kink button there, then and you divide it in 1, then it will basically it'll basically give you your corner points only. And then I can redraw a polyline through it, and now I have a polyline that only has 4 control points. Then I can explode this one into its line segments, and what I have now is basically all my edge. Let me show you. Now I basically have my continuous edges for all of these as a continuous line. Whereas before, I would have, well, it's because it's not flattened. If I flatten this, I would have smaller line segments, I believe. Oh, sorry. Yeah, well, they're joined. Yeah, anyway, it doesn't matter. What I'm getting here at the end is separate lines for each of my edges. So that kind of works. Then I need to find overlapping edges only. So what I'm looking for now is this edge here is shared by the topology A plane and the topology B plane. The outer edges are not. So what I'm going to look for is for the edges that exist twice in my data set. This is a dirty way of scripting this. I don't know any better ways to do it. If you have any ideas to find identical curves and identify them and extract them, let me know. But the way I work my way around it is I identify the middle points of all of my curves. And then you'll see that if a curve exists twice, that number will be there twice. So I say, for example, well, let me sort this, then we'll see. See, some of these lines occur twice, 0. Oh, bullshit. Okay. Well, I'm not explaining it very clearly. Anyway, what I'm looking for is my points that occur twice in my data set. So a trick around that is if you create a set, then you can, with the CSet button, which you have here, you can create a set with all the distinct values only. So what I'm doing here now is, so in my original set, I have 23 values. Now I know that there's actually 16 instead of 24 unique values. So I have 16 unique values. And then what I'm doing is I'm looking into my, with the button over here, I'm looking into my set over here on which indices these unique values appear. Aman, did you send me a better version?
I was trying something. I mean, you can have a look at it when you have time, of extracting the two sets of curves.
Okay, let me open it up in a bit. Let me first go through this one. So what we're getting here now is the indices where certain points appear. And you see some occur only once, some occur twice. So then I can just take the item on location 1 from all of these, and basically what I'm getting is all my edges that are occurring twice in my data set. So that's kind of the idea. So these edges occur twice in the data set because their middle points occur twice in the data set with the middle points. That's it basically. So here now I have my clean edges only occurring once. And then I need to find the end points of all my curves that are on top of these lines. So I can find all the endpoints of my curves. I can check the distance to my curve set here. I can sort them based on distance 0, and then I can basically call out the points that I have here. So now I have found all the endpoints of my curves that are taking place, that are placed on top of, switch this off, that are placed on top of my joint edges. Yeah, so these are the points that I need to evaluate. And each and every one of these, I need to make the assessment on which ones to join. Any questions?
No, good so far.
Okay, hold on. Let me, 1 second. Okay, so then with this we go into the loop. I'll show it first for only one, and let me see how I can do that. So I'm going to bypass the loop for a second. So I'm going to bring D0, I'll bring this one in here, and D1 I'll bring in here, and I'll need to bring D1 further back in here as well. And D0 I'll need to bring over here. Well, let's go over this setup. So what the system does is we're breaking up our setup. So from my list of curves, from my point lists that I have, these are all the points I need to work with. I'll take the first one, which is the live points that I'll be working with. So that's my live point that I'll be working with. And then what I'll do is for my current curve list, which is the curve list with everything in it, I'll identify which curves are going through that one point. So what I can do is find the curve closest point. Whenever that distance is 0, I can call using that information. So what I'm doing here is I'm identifying which 4 lines are going through that setup. Then I need to find the vectors of these lines. So the first thing I need to do, I don't know the orientation of these lines. It could be that they're oriented this way or that they're orienting this way. So the first thing I did is I flipped. I don't even know if I need to do that actually. Do I need to do that? well, I did it anyway, so I don't know if I need to do it, but anyway, I've done it. What I did is I flipped all the curves to make sure that the curves are oriented all in the same way. Maybe that's the necessary step, let's see. And then I'm evaluating my starting point, my live point here on that curve to get their tangent vector. So if I go into the display vector button here, what you see is I'm getting all my 4 vectors here. And then I have to choose how to combine these curves. And there's 3 ways. So if I hold on, let me do something for a quick second just to make it easier to explain. Oh, all right, flatten, and make that a little bit smaller. Oh, so I can choose to combine I can choose to combine 0, 2, and 1, 3, 0, 1, and 2, 3, or 0, 3, and 1, 2. So those are the 3 ways that I can combine these. And what I'm doing, I'm basically calculating the angle between 0 and 1 and 2 and 3 in the first batch here, 0, 2, and 1, 3 in the second batch here, and 0, 3, and 1, 2 in the third batch here. And then I'm taking the mass addition of it. So what I have here at the end is basically 3 number values for this point right now, which is the mass addition of the angles between these two. And then I can sort those from large to small. And I need to take I'm reversing my list here, and I'm taking the first one. So I'm going for the biggest one. I want to have the biggest angle between both of them. So right now, this one identified 4.18879 is the biggest one. Now, in order to know, I probably did a rather clumsy way to identify these numbers. There must be a faster way to do it. But what I did is I kept track of these types of operations here by using a little text string that I generated. So I produced these little texts, which are basically the titles of my tabs here. 0, 1, 2, 3, 0, 2, 1, 3, or 0, 3, 1, 2. I just generated that using a simple series button. So this is just text that I have. It's basically the titles of my 3 blocks here. So I'm sorting that simultaneously with my angles. So right now I know that an orientation of 0, 3, 1, and 2 is the best way to connect my curves. So connect curve 0 with curve 3 and curve 1 with curve 2. So I've just sorted that in a similar way as I've sorted my numbers here. Is that clear? And then what I can then do, I can split this text using the separator that I have. And now I know that I need to take from my original list, from my curve list that I had over here in the beginning, I need to take the first and the third, and then, sorry, the 0 and the third, and then the 1 and the 2 to join. So what I'm getting at the end here then is, this is 1, curve 0 and 3 are being joined, and this is the other one. Oh, shit, what did I do? Okay, sorry. And this is the other one. So I'm joining them correctly. So the little trick that I did is I'm just using text to identify which ones I'm selecting, and that kind of works. Clear? So then these 2 curves are the curves that I now need to add into my list. So these 2 curves I need to add into my bag of curves that is going through the loop. And the 4 curves that I had originally, I need to remove from it. So let me have a quick look here. Let me zoom out.
I couldn't understand the criteria of the sorting.
Okay, so let me go through that again. So what I've done here, so there's three ways that I can combine my lines, right? 0, 1, and 2, 3, which would be this one and that one. So that's this one. I could do 0, 2, and 1, 3, which is this one and that one. And I could do 0, 3, and 1, 2, which is this one and that one. And what I'm doing is I'm always calculating the angles that I have around these points, right? So in the orange one, my angle will be close to 180 degrees, say, on my screen. Whereas in the green one, it will be close to 60 degrees. In the red one, it will be close to 120 degrees. So what I'm doing is I'm doing a mass addition of that over here. So now I know the mass addition of my angle. So for orange, that will be close to, say, pi, or sorry, 360 degrees. For green, it will be twice 60, so it will be 120. For red, it will be 240 degrees, right? So I can sort that. So let me just write that down. So for orange, let's say it's 360. For green, it's close to 120. If I add it, so if this is 60, let's say that the orange ones are 180, and then the red ones are 120. So we end up at 240. Yeah. So I'm sorting that, and from that I know that I need to take this one. I need to take 360 degrees. But I also need to, so now I know what I want, but what I need to know, I now need to identify the three curves, or the two curves that come with it. And I just use a simple trick by, here I'm sorting my data, but with it, I'm also sorting a text file. And the text file I'm sorting with it is what I've circled around here, 0, 1, 2, 3, 0, 2, 1, 3, 0, 3, 1, 2. So that's a text file that I've produced underneath here. It's just a little text file. So by creating then the first item of my text file, I'm actually selecting 0, 3, 1, 2. And then with that information, I can just split it up and select curve 0 and curve 3 and join them, curve 1 and curve 2 and join them. Does that make sense?
Yeah.
Yep. Yeah. Thank you.
So
Thank you. Now it's clear.
no, it's fine. It took us some time to get to that. It's quite logical in principle. So that's what's happening here. So just to let you read it. So here, these are the sums of the angles that I've sorted. These are the associated indices that I have. And I want to get the first one, which is 0, 3, 1, 2. So I'm splitting this up now with using my underscore here. So now I know that my first curve index is 0. My second curve index is 3. This one is 1, and this one is 2. And then I know that for my first joining, I need to take the first 2 points here. So these two, yeah, are coming from the first and the second. And I'm joining these two, and I'm joining these two lines, which gives me the green curve now. And then here I'm taking the bottom 2 points, and that gives me this one here. Yeah. So I've just joined them based on this angle evaluation. Is the principle clear?
Yep. Yes.
Yeah.
Now it's clear, honestly. Yeah.
Okay. Good. It's the first time I'm teaching this, so I need to let me know if I need to clarify things further. So once I have this, then I need to jump to my next point, right? So this live point is no longer live, it's taken care of. So that one needs to be removed from my point list. And the 4 curves that I have joined here need to be removed from my curve list. And the 4 original curves that I've joined need to be removed from my curve list. And the newly joined curves need to be added to it, right? So that's what I'm doing here. First of all, on top, this is my point list that I had in the beginning. I'm culling my first point. So let me just, hold on, let me hide this for a second. Let me hide these. Preview off. So that's my original live point. In my culled item list, that point is no longer there. So I'm just removing that one at the end. So you see, my itemized list is updated. And then the curves that I had, I'm deleting the ones that were selected originally. So these 4 curves here that I had in the beginning, I remove from the list, which is the list that I have made here, and I'm replacing them with my newly joined curves. So it looks the same, but now this one is connected to that one is connected. And I'm merging these two lists. So now, if I would look at this, let me quickly visualize that. You'll see that, see the yellow lines, these are actually connected, but all the other ones are not. And then I just repeat this whole operation that I've just done. Only this time, I will jump to my next first point, and I'll work with the new bag of curves that I have. So this goes into my loop, and then the loop basically brings it back to the beginning over here, and the whole thing restarts. So then it loops and loops and loops and loops. There's two ways to stop it. Either you stop it when you don't have any points left in your live points bag. So with my list of points that I have here is 0, then this Boolean value will become, so right now I still have 15 points in my list. So this is not yet 0. So I'm not yet exiting my loop. So it's going to go back and it's going to keep on looping, looping, looping until I reach 0 points that need to be joined, and then the script is going to continue from here. Yeah. A quick, tiny. Any questions there?
No.
Cool. A tiny trick. So in the beginning, you kind of need to set how many iterations you maximally want to do, and ideally that's the amount of live points that you have. Just as a safety mechanism, I doubled that. Not that it would make any difference, but at least if it's up to the loop, it will do it 32 times, and then it will just get cut short once my numbers are depleted. Yeah. So let me close this one and reopen it again so I have the clean version. So yeah, so that's what's basically happening here. And let me see. Yeah, so it automatically runs through this very efficiently. So now if I open my new Rhino file with my W column in here as my input, let me let it run for a second. Nope. There you go. So now it's done that immediately for my other setup that I have here as well. And it's not looking super good. So let me increase my resolution here to something higher. And now it's looping again. It's going through the loop. And now you see it kind of works very well. And this becomes very effective. I can just copy my surfaces here, put one over here, and it will just run it again. And now I have a triangulated singularity here, a hexagonal singularity over here. So yeah, and it will just do this in real time, live for you. Cool, right? I got very excited when that one finally worked, because up until then we were grouping everything by hand, which also works. It's just not that fun to play with. Any questions at this point in time?
I'm just wondering why you had to use the loops. Like, didn't you find any other way with conditionals? Like, I don't know.
Like what? Tell me if any brainstorming can really help. Like, I know this step always felt a bit contrived to me. It works. We've tried a few different things. Like in the beginning, we were working with X, Y, Z directions. For example, all the curves that are going in the X direction, join them and then go to the other direction. But then we started to run into design problems if we wanted to arrive at different setups like this one here. Because right now we have full flexibility. I can rotate my planes in any direction as a starting point, and I can start to work with that. So, yeah.
I'm just wondering, because you're looking for the angle, which is 360, and you know, like the angle that you want. So why we don't use, like, if this like angle equals 360, just join just join these members. If they don't, just like disregard, instead of going in one loop and then in another loop to cull the items.
Well,
I might
say that again. I'm not following with the question. Can you repeat?
Like, No, I'm just like, because we know that if the members had like 360, like if we like you explained now the angles, how
Yeah.
it works.
Yeah.
So if we know this, like why don't like we just ask the grasshopper with conditionals if this like this angles equals 360, just like join these members. If they don't, just like disregard the
That's kind of in a way what's happening, right? Like this loop is basically a conditional loop. It's evaluating 3 scenarios and it's picking the one that makes most sense, and then it goes through it. Because if I look at what I have on the screen right now, if I look at this line here, let me draw on it. This one has been joined 1, 2, like this one has been joined with the algorithm here. Let me switch these on, hold on.
I see. Okay.
This one has been joined 3 times. Has been joined there, there, and there. And that's where it becomes tricky. That's why you need to have this live system that goes through all the points one by one and gradually updates it. Because it's not a linear thing anymore. The outcome from one joining needs to become the input for the next one.
Yeah. Okay. Got you now. Yeah. Okay. Okay. Makes sense. Thank you.
Other questions or comments? As mentioned, I'm totally open to any suggestions to make this more.
So I kind of have an idea, and I'm just the one I sent you had some flaw, but I think I have an idea.
Yeah.
If I'll try it out during the break, and if I'm able to figure it out, I'll definitely share it.
Yeah. Okay. I was actually thinking of having a little break now, for say, maybe 20 minutes, something, or 15 minutes, 20 minutes. Yeah, let's come back at 11:20 Hong Kong time, so 20 minutes from now, unless there's any questions still at this point in time. I think it might be good for you to have a quick look at the script and really try to figure it out if it's the first time that you're seeing these loops in action. Try to make it work and maybe play around a little bit by copying these surfaces. An important thing to note, the orientation of these planes, it's important that they are all identical. Like if you would flip the orientation or rotate, say, one of the green planes, then in the beginning here, the data structure that the diagrid produces will change and the connections will be wrong. You'll start to see, not in this example here, because all the surfaces are nicely separated, but if you have a longer plane of, say, red squares next to each other, all of a sudden your curves will start to join in a zigzaggy way. So as a design restriction or rule, you need to really work with exactly these planes that you have. So yeah. Any other questions or points at this point?
No.
No. Okay. Let's come back in 20 minutes. I'll see if I can find the not video, and then we're gonna keep on going.
All right.
All right. See you in a bit.